And I'll share my computer screen. First exam is March 9th. I think it's March 9th, right? Hold on, let me look. Not next week, but the week after. Oops. Yeah, March 9th will be the midterm exam. Is there a quiz today? I don't know. I don't know if we're going to get to the material that's on the prepared quiz. If we don't get to it, then we won't have it. But I think we will. I think we will. But I'm not positive about that. Okay. So I answer those questions. Yes. If we don't have a quiz, we're gonna do like a in-class questions, in-class quiz, not the kind that we've been doing. We all work together on this quiz. So this is where we left off last time about using the formula the formula which I have written over here to calculate the resistance of a piece of wire. Okay, and the resistance that a piece of wire provides to flow of electricity, in other words, it slows electricity down, is depending on what the wire is made out of, like for example, copper. So this is called the resistivity. The length of the wire, how long is it, and basically how thick is it, how thick the wire is. This circle, what's the radius here? And if you use the formula, we did this problem last time, if you remember, that's where we left off. We used it to calculate the resistance of a particular wire given these dimensions. Today we'd like to look at a little problem where we're going to look at different wires of different areas and different lengths and compare them. We won't calculate what R is, just want to compare them from smallest to largest, like for example this problem over here. All right, so we have all these wires. They all have a particular diameter. These two are the same diameter. These two have twice as big a diameter and different lengths. But they're all easy numbers. They're all multiples of one another. And we're going to use this formula. Now, we don't need to use the formula here because basically what the formula tells us is that this is equal to rho, which is the same for all these wires. Rho is the same. And divided by the area, where we know the area is pi r squared, pi d squared over 2. This is the diameter. So pi d squared, I'm going to take the pi out over here and put it over here. D squared over 2. D over 2, I'm sorry, squared. Because pi r squared is the area of a circle. So you're given diameter, so the radius is half the diameter. So pi over 2 squared. So we don't need to be concerned about these because it's the same for every wire. Rho is the same, pi is the same. So basically to put these in order from smallest resistance to largest, all we got to do is look at this. So let me erase this since we don't have to worry about it. On the eraser. All right. So this is all we're going to look at. So for example, let's do that for this first wire. L, so rho, R here is going to be, I'm going to say proportional to L divided by D over 2 squared. That means D over 4. So this would be D squared times 4. Okay. Let's do the same thing over here. Again, we're going to look at L. In this case, it's going to be 2L divided by same as d squared here, which is d squared over d over 2 squared, which is going to give you 4 on the denominator, and you have 2 on the top divided by 1/4, which is squared. So 2 divided by 1/4 here is giving you 8 L over d squared. Let's do the same thing here. So this one here is going to be 2L, just like it is over here. But now the area here is bigger. Don't forget, a bigger area means it's easier for current to get through here. You can look at this as water flowing through a pipe. If it's a bigger pipe, it's easier for the water to get through. Same thing with current. It's easier for, that's why you have it in the denominator. All right. So I messed up an L here. How do I do that? So it'd be 2L. Again, we're using the same formula divided by D, but this is 2D. Okay, 2D squared. So this will give you 2 over 4. So this will give you 1/2 L over D squared. So this is resistance is low because of this humongous hole here, circular area. How about this one here? Okay, so this one will be L, and it's also without the, this was, oh, I forgot the 2 here. Okay, hold on. No, it's all right. I got the 2 there. So this will be 2L. I'm sorry, this one will be just L, not 2 here, divided by 2D squared. And so this will equal to 1/4 L over D squared. So here you have them. Each one's a little different. This one's 1/2, this one's 1/4, and this one's 1/4 also. No, it can't be, these two can't be the same. I must have made a mistake here. 2L over 2D squared. That's 4. 2 over 4 is 1/2. L, because I'm sorry, no, it's right. These two are the same because the L makes up for it, right? So these are, you can see how big they are in relation to one another. Of course, this one has the smallest resistance, 1/4 L over D squared, and all of these are a little bit bigger, 1/2, 8, and 4. Okay, so that's one way of looking at this formula, how these variables affect the so here's a little example of just using the formula to get a number for the. We already actually did an example of this, but this one just using it in a different way. They're giving you the resistance, they're giving you the length, and they're asking you to find the length, how long. So basically, you're using this equation here, the same one we've been using, and you're going to calculate L in here. Right? So if you solve this for, you can just put in everything else. So for example, how long to have a resistance of 0.1 ohms? So basically, he's doing it in blue, so let me do it in blue. 0.1 is equal to rho. This is copper wire, so rho is 1.68 times 10 to the minus 8. And the units for rho, ohm meters. times the length, which will be in meters. It's 100 meters divided by the area, which is pi d squared, pi d over 2 squared, pi r squared, so d over 2 squared. And you have to solve this equation for d. It's a little calculations, I know, but let's just make sure that, so this will be meters squared over here. The units will be meters squared. Pi has no units. If you square the distance, you'll have meters squared, and you have meters squared on top, so they will cancel. Meter times meter, cancel this meter squared. So the units come out. I'll show you the calculations. I have it over here on the side. They're a little hairy. Let me put it over here. Okay, so we're using this, the area is pi r squared, r is d over 2. Okay, and if you solve that equation for d, don't forget you got to take the square root, solve it for d, you got to take the square root. You will wind up with d being this, and putting in all the variables that we just had, comes out to 4.6 millimeters. So this will actually come out to 4.6 times 10 to the minus 3 meters. But it could be done. So the length of a copper wire is cut in half. By what factor does the resistance change? So this is pretty easy. If you look at where I put the formula, so I can just copy it. No, not there. Yeah, let me just write it. Oh, here it is. Okay. So the resistance is given by that formula. The length of a copper wire is cut in half. So R now is going to equal to this new R. It's called R prime, is going to equal to rho L over 2 divided by the area. So this could be rewritten as 1/2 rho L over A. So the answer to this question is, by what factor does the resistance change? Anybody? How does this number compare to this number? Isn't it half of that number? This is 1/2 rho L over A, right? Yeah, I know. We just did a hard problem, and now all of a sudden I'm doing an easy problem, and you don't believe it. It wasn't hard. It was only hard in terms of calculations, right? Okay, so let's look at this. So this is another 122. Using the formula, to calculate the resistance. We'll just set it up. We won't do it because it's the same as any other problem. The trick here is that this is in centimeters. So don't forget, when you use the formula, because resistivity, rho, is in ohm meters, right? So the distance here, the radius must be all in meters. Everything must be in meters. The length is in meters, the resistivity is in meters, and the radius must be changed to meters here. So we're not going to spend time doing this, or the math, but I'll just show you the calculations over here. So you notice the area here, pi r squared, okay? We have to change the r from 5 to 0.05. meters squared. And E would then turn out to be the right answer. So this is the same one. We're going to skip this with the same one as we had before. So let's go on to this one slide here. This thing we call resistivity of a wire, which depends on what the wire is made of, but it also is affected by temperature, it turns out. That when a wire gets real hot, its resistivity changes. So this is the formula that it follows to change. And that means the resistance changes, okay, by the temperature. So usually the temperature we're talking about, if we ignore temperature, room temperature, 20 degrees Celsius. But if it's very hot, a very high temperature or very low temperature, this resistivity will change. Now, basically, resistance, you can put resistance into a circuit, just plain old resistors, in order to control the current. And the resistors look like this. Okay, but the resistors can also be a lamp, or a resistor could be a heater. Anything can be a resistor, anything that eats up energy. But these things are just wires wound around inside here, a particular length. They're usually copper wires. And depending on what kind of resistance you want, there's a length here involved inside these things. You don't see the wires wound here, but they are. So electrical resistance is measured in units called ohms. We already saw that mentioned before. And the symbol for that is the Greek omega. The ohm is that amount of resistance when a volt results in a current of 1 amp, as we discussed what current is. That amount of resistance when a volt results in a current of 1 amp. So an ohm is a volt per amp. How many volts per amp? How many volts of resistance per amp? So we were talking about how to measure electric current, but we know that electric current is related to two things. It's related to the resistance to flow of current, and it's also related to the voltage. That's the thing that's pushing basically the electrons around in the circuit. So it's related to them. And Ohm's law, it's called Ohm's law, derived the relationship between these two. That means the more voltage you have, that means the more current. Because don't forget, voltage is what pushes electrons through a wire or through a resistor. And the higher the resistor, the less current. So resistance slows down. So your current is inversely proportional to the resistance. That means the bigger you make the resistance, the smaller is the current. Putting those two together, you result in Ohm's law. There's a current flowing through a circuit, and I'm sure you did this already in lab, or writing it a different way. The voltage across a resistor would be the current going through the resistor times the resistance. So for example, let's say we have a 1 meter long wire is connected to a 12-volt battery. 20 coulombs of charge flows through it in 0.1 seconds. What is the resistance of the wire? Well, you would think you would have to use one of those formulas, but you don't really, because all you got to do is use Ohm's law based on what you're given. V equals IR. You're given V and I, 12 volts and 2 amps, and the resistance is 6 ohms. So this is a way of measuring the resistance directly. You don't have to calculate it using that formula there. So, and by the way, the current is not given directly, but it tells you 20 coulombs of charge flows through in 0.1 second. So the current, don't forget, we discussed this first formula. The definition of current is the amount of charge, rate of flow of charge. The charge flowing through divided by the time. So in this case, that would be 20 coulombs in 10 seconds. It gives you 2 coulombs per second, or 2 amps. That's why you have 2 amps over here. So this basically, Ohm's law states that the relationship between these 3 variables here, V equals IR, is a linear line. Is linear. In other words, if you make a graph of current versus voltage, you should get a straight line. This is true in most cases, but you have some materials that don't follow this. It's curved. So Ohm's law doesn't apply. An example, a diode is a common example of a non-ohmic device where Ohm's law does not apply to a diode. So let's see if we can do a couple of examples of using Ohm's law. It's not very complicated, it's pretty easy. So anything that uses up energy in a circuit is a resistance. A flashlight. A flashlight uses energy, obviously it lights light. So it has a resistance. Let's say a resistance is 25 ohms, and if you connect it to a 120 volt source of voltage, which is your household voltage, what is the current flowing? So this is a classic example of using Ohm's law. Let's see who can get this first. So both of these are given here, volts, ohms, that's R. You can do this in your head. Almost. Yep, B is the right answer here. So it's just your basic, each problem here gives you something a little different, but using the same formula. So here, you're given 2 other things. So you're given the voltage, or you're given the current here, it's 0.7 amps. And you're given the resistance, and you're asked for the voltage. Sorry, it's on the bottom. So this is equal to 49 V on top, yeah. V over 490 is equal to 0.7. Yeah, this should be down here. Yeah. Let me just erase it. So I think I have the solution here. Yep. So solving this for V equals IR, 0.7 times 490 is 343 volts, and C is the right answer over here. And I think there'll be one more problem, sort of finding the third thing. What is the resistance of a rheostat coil if 0.05 amps flows through it when 6 volts is applied? So again, this is the same formula. This time you solve for R. Okay, so R is equal to V over I, 120 ohms. So an interesting problem occurs here. We were talking about how good a conductor is a human being. Under normal conditions, a normal human being It's not a good conductor. It conducts electricity, but it's not good. It's not particularly good. So at this point, I think we can actually look at a film that I showed you the first part of it a couple of weeks ago. I think we can now look to the other part of it. If I can find it here, I should have had it prepared. So it'll be either in 1819. Okay, I can't find it, but I know it's here somewhere. Wait a minute, maybe in my astronomy class, I may have moved it there. Bear with me here a minute. It's a really nice film. That's what I'd like to show to you. How did I lose it? Well, I guess I'll have to show it to you some other time. Let me just make one more effort here. Did I put it in the films folder here? So one more way of doing it, see if I can open a player. Ah, here it is. Okay. All right, I got it. It's a nice film. That's why I want to show it to you. I took a long time in getting this. Rewatch the beginning of this film. You're going to see the same guys, but he's 20 years younger in this film. Okay, so let's take a look at this.
Safely touch a flashlight battery? Yeah. Can you safely touch a 9-volt battery? Yeah. Can you safely stick your finger in the outlet? No. So if you can't touch 120 volts, should a person touch 200,000? Probably not, but do you want to see it anyway? That's what I was afraid of. So first, before we do this, I know it's not off. But there is something I am off. I don't want to be. The ground. What's this? Stool made from, which is an, I'm going to get on the stool. Not because I'm short, but because I want to get away from the ground. But if I'm down here, the only insulation I have is whatever's in my shoe. Not that much. If I'm up here, I've got my shoe, and I have 9 inches of plastic, something like that. Hopefully, it's enough insulation, the electrons won't flow through me and into the ground. They'll just gather on me. If they just gather on me, what should happen? What hair I have left should stand up. Yes. 3, 2, 1. Ah! Got it! Doesn't hurt. Anything happening? I'm hoping hair is doing something. But at any rate, I'm not dead, which is a good start. Right? Now, how many volts are on my left hand? How much is the bunch? About 200,000. What'll happen if I touch the dome with my right hand at the same time? Nothing. Why does nothing happen? How many volts in my left hand? 200,000. How many volts in my right hand? 200,000. What's the difference? There's no difference. Electricity flows from high voltage down to low voltage. If it's the same voltage, it doesn't move around. It's like having a bathtub full of water. If all the water's at one level, the water stays put. Have you ever seen birds on the power lines? They don't get killed. Same reason. Both their feet are at one voltage. They might get a little bit puffy, but they don't get killed. Now, what would happen if instead of this dome, I touch the grounding dome with my right hand? How many volts would be in my left hand? 200,000. How many volts would be in my right hand? Ground is 0. Defined as 0. What's the difference? 200,000. That's like a waterfall. Okay, the electrons will flow from a high voltage down to a low voltage. In fact, if you listen carefully when I point at the dome, what's that sound? Yeah, those are electrons flying off my finger. You'll notice, watch my hair when I point. Why does my hair go down? Yeah, if the electrons are flying off my finger, they're not on my head. They make my hair stand up. And you'll notice it also doesn't do it when I make a fist, but it does when I point. It turns out charges jump off of points each, and they jump off around things. That's why these things are round, to gather the charge. You know what a lightning rod is? What's a lightning rod? Pointy piece of metal. People think it's there to attract lightning. It's actually there to relieve charge, wait till lightning doesn't strike. In my pocket, I have that nail. It's like a lightning rod. If I let go of the point, if your ears are good, you can hear it whistle. If your eyes are good, you can see when I cover the point, and I let go of the point, my hair moves up and down. Don't know if you can see it, but I can feel it. I can feel it moving. It's more obvious, though, instead of pointing at the audience, I point here. Okay, so again, why is my hair going down? I'm losing electrons. The electrons are flying off the nail to the dome. And if I get it close enough, we can actually make a little spark that we can see better if Mr. Dave turns the lights off. A little spark. Lights back on. So that little spark tells you something. For there to be a spark there, the electrons have to come from the dome through me, out the nail to that dome. If electricity is flowing through me, why am I not dead? I'm not insulated. That's the ground. I'm touching the ground. I'm not disappointed, I'm just confused. Why am I not dead? Well, I mean, if you like, I can come down here. What's my hair doing? Nothing. Where's the electrons going? Through my feet into the ground. If I get up here, I block them. So electricity is flowing through me. Why am I not dead? Again, this is not a major disappointment on my part. But why am I not dead? You know what current is? Like in a river, what does current tell you? Yeah, which way and how much? Okay, which way is the water flowing and how much water is flowing? For electricity, what does current tell you? Which way and how much? Right, is this a high current or low current? It's low. That's why I'm not dead. There's just not that much electricity flowing through me. If this were a high current, what would happen? Yeah, I die kind of in a gross way. Have you ever put the hot dog in the microwave? Ever forget to poke holes? What happens if you don't poke holes? It blows up, right? Because the water inside changes steam and it needs to get out somehow. Well, this were a high current, the same thing would happen to me. My blood would boil, and I'd blow up all over the room, which being an experiment you only do one time. It's also why you don't stick your finger in the outlet. Even though the outlet's only 120 volts, it's a high current. It's really the current that gets you, and not really the voltage. Now then, what'll happen to my hair if I let go of the dome? Stay up, mostly. How come? I'm insulated. I'm insulated. There's nowhere for the electrons to go except from the water vapor in the air. If I want to get rid of it quickly, what do I need to do? I need to step up. And as soon as I step off, I get a shock to my foot, and the electrons lead me that way. By the way, this is how a lightning rod works. Here's your thunderstorm. You have a lightning rod. You bleed off the charge, lightning doesn't strike. Your neighbor doesn't have a lightning rod. They get fried. You're fine, they're not. You're fine, they're not. So that's a little.
Okay, so I hope you enjoyed that. So this sort of is what we're talking about right now, the flow of current across a difference of potential. And so the example that he was showing there, the current flowing through a human body, it's going to depend what the resistance of the human body is. So at a resistance of, say, 100,000 ohms, what will be the current in your body if you touch the terminals of a 12-volt battery, like a car battery? Well, this is normally what your resistance is under normal conditions for a human, and the current will be the voltage divided by the resistance, which is 12 volts divided by 100,000 ohms. This is not a lot of current. All right, 100,000. This comes out to 5 milliamps. 5 milliamps. Now, you will feel this. You feel a little shock, but you won't die and you won't get paralyzed and nothing bad will happen to you. You just feel a little. But supposing you just stepped out of your shower, or maybe you're still standing in a puddle, what happens is that your resistance now becomes only 100 ohms. So the current now is going to be 12 divided by, not 100, 1,000 ohms, which is 12 divided by 1,000. And now this will be 12 milliamps. Now this is now a little serious. I'm going to show you in the next slide how many amps you need to injure yourself. This won't kill you, probably, but it'll give you a good shock. All right. So here is a little table of how much current do you need to be, first of all, to be felt, just to feel a tingle. Basically, it's 1 milliamp. So the previous question, you had 5 milliamps to start with. Okay, 1 milliamp, you can feel it. 5 milliamps, you can not only feel it, but it hurts. 10 milliamps, well, this causes involuntary muscle contractions, spasms in your muscles. Like, if you ever did this to a frog in biology class in high school, you saw the spasm in the muscles. 15 milliamps causes loss of muscle control. And of course, 70 milliamps through the heart, probably fatal. Okay, particularly if it lasts longer than 1 second. If it's like a tenth of a second, you may survive it. But if it lasts a second or more, then this will probably kill you. That's what he was talking about. How come I'm not dead? So, I know you guys have been building circuits in lab. Unfortunately, they're much more fun to actually do it in class. So basically, anything you put in there, like a light bulb could be in the circuit, just a resistor could be in the circuit, like over here. And of course, you use meters to measure various things. An ammeter is used to measure current. And in order to use an ammeter, you must break a circuit somewhere and put the ammeter in there. And a voltmeter is used to measure voltage. Don't forget, voltage usually is the difference in potential from one place to another. So basically, you have to put it across something where there is a difference of potential, like, for example, a light bulb. So let me just briefly show to you in using the same simulation that you guys were using in class. So here is a circuit setup. This is a battery here, and it's 10 ohms. I'm sorry, this is a resistance here. This is a battery on top over here, and it's 9 volts. Let me change it to to 20 volts. Okay. Now, right now, current is not flowing. If I close the switch here, current flows. And this is what's called conventional, which means you're looking at the flow of positive charges. The flow of positive charges go this way. The flow of electrons, which are the things that are actually moving, go the other way. But it actually turns out it's a good idea that we use the direction of current as the flow of positive charges. So in any case, if you want to measure the current, you must break the circuit, put in between here an ammeter, and there you measure the current. And this is Ohm's law. Don't forget, this was 20, the battery was 20, this was 10, so 20 divided by 10 is 2 amps. If you want to measure the voltage, you have to measure it across something. Like, for example, if you measure the voltage from here to here, this actually gives you the voltage difference. There's no voltage difference. But if you want to measure the voltage, first of all, let's say across the battery, like I have here, you can put this anywhere over here or here, all right, or even down here, until you get to the resistor, all right? So you measure the voltage across here. You can measure the voltage across the resistor, okay? And the voltage is the same because this is the only thing that's flowing in this circuit. So if you open the switch, current stops flowing. You need a complete circuit for current to flow. So those are examples of using meters. Let me move this back here. So how do you find electric power, which is basically power is defined as work done per unit time. Now you may have done a little bit on power in physics 1, maybe not. You may have not gotten to it, but basically power is work divided by time to do that work. So in let's say the power of a machine that lifts a weight and puts it through a particular distance, the work it does is force times distance. The power is the work done divided by the time to do that work, the time to lift this up here and put it on top. That's power. How long did it take you to do that work? Now we can write a couple other equations related to power, knowing that the work done is also the energy. The work done is also given by Q times V, if you remember. So we substitute Q times V for W over here. We get, and Q over T here, Q over T is just current. That's how current was defined, if you remember. And so we can substitute I into the equation Q for Q over T, and we get the power. And this is the power utilized, for example, in lighting a light bulb. You can find the power in utilizing the light in lighting the light bulb by multiplying the current running through the light bulb multiplied by the voltage across the light bulb. So you have a light bulb over here, let's say, in a circuit. You have current coming in here, and you have voltage across the light bulb from here to here. There's a voltage, which means the current does work as it goes across the light bulb. That's why we say this is also a resistor. So one way to find the power utilized by this light bulb is to multiply the current running through the light bulb multiplied by the voltage across the light bulb. Now there's a couple of different ways you can calculate the power in a accessory like this. So basically it says what happens if the current is increased or the voltage is decreased. Well, if the current is increased, the power utilized by the bulb gets more current, more power, the brighter the light bulb. Now, as I mentioned, there are a couple of different ways of writing it. I over V is equal 1. Now, the units for power are watts, okay? A 60-watt bulb, for example, what does it mean? It does 60 joules of work per second, okay? So that's called a watt. So another way utilizing Ohm's law, we can replace I here with V over R. So we have V over R times V, which is V squared over R. So this is our second equation for power. And there's one more. Again, we have I over V, but V is equal to IR. So basically, if we plug that in for V over here, IR, we get I times IR, I squared R. So this is our third equation. And if you have to calculate any kind of power, you use whatever is available. So for example, let's say you want to find out the power delivered by a battery. Normally, you don't have the resistance of a battery, so you want to use the equation that has something like this: the current that the battery delivers times the voltage of the battery. Okay. So, but anyway, you have three equations, and we'll do the practice problems here. So energy, basically in a circuit that's running electricity, running current, basically what happens is this. Again, we look at current flow, the direction of current flow as the direction of positive charges. So the way you draw a battery in the circuit is you draw it over here with the longer leg, or longer side is the positive terminal of the battery. And what that means, positive charges go through here, and as they go along here, when they start, they have a lot of energy. How much energy? Well, if this is a 12-volt battery, they will have 12 joules per every coulomb that flows. 12 joules of energy for every coulomb that flows through here. Okay. Now, as they have all this energy, but when they come up here, they lose energy as they go through a resistor. They lose energy. And they come down here, they've actually, in this particular circuit, they've lost all the energy. They're back on ground. Ground means zero energy. But the battery gives them energy again, so they can come up. It's a good way of looking at it. Now, if you have two resistors connected this way, one after the other, we call the series resistance, then what happens is this. The amount of energy it has right now is 12 volts. As it goes across this resistance, it loses some of that 12 volts, but not all. And then it loses the rest of it as it goes across this one. It's back to zero energy. So we can look at current flow from this energy perspective. And as I mentioned before, if we define the direction of current flow as the flow of positive charges, this makes life easy, because then we can consider this like something dropping from a high voltage to a low voltage. It's like from a high height to a lower height, and then even lower height, and back you're on the ground. So just summarizing all the equations that we had here. I think I've used all these already. They're over here. The three equations for power are given over here. Now here's a good little problem. It is observed that a light bulb is rated at 60 watts. What does that tell you? Well, there are 60 joules of energy delivered to the light bulb every second. That's what it tells you. Power is work per time, or energy per time. So let's look at a 120 watt bulb. Okay, 120 watt bulb. It draws 120 joules of energy every second. 120 joules. So the power and voltage, say on the light bulb, this is the light bulb that's connected to your household current. That means it's 120 volts. It's a 100-watt light bulb. How many amperes will flow through this bulb? Well, this is one of the equations that we had over here, and obviously, which one do you use? You want the one that you use, the one that has I and V in it, because this is what you're given here. It means this one here. Okay, power here is given, and you're going to solve this. Is 100 watts, so this is a 100 joules per second. Let me write it in joules per second. That's what a watt is. And you want to solve this for I, if the voltage is 120 volts. And so I is equal to basically 10 divided by 12, which is 0.8. 10 divided by, this is 10 divided by 12, 0.8 amps will flow through, if this is connected to household current, to this bulb. So basically, a couple of problems where you are you have to choose one of the equations to answer the question. And again, which one you choose depends on what's given here. So for example, a toy car, electric motor, resistance of 17 ohms. What is the power delivered by a 6-volt battery to that toy car? So P equals, you're given ohms, and you're given voltage, so you're going to use obviously this equation over here. So let's see if you can use it. Let's see, V squared, it's 36 by 17. So that will be B, right? Yep. So that will be B, 2 points. It's about 2, a little bit more than 2. So that would be B, would be the right answer here. And each one of these questions here, we won't do them all. We just set them up. Again, we're going to figure out a different equation to use depending what's given. So here you're given the resistance and the power, and you have to find current. All right, resistance, power. So obviously it's this equation over here that you're going to use this time. And so here basically is the calculation. So solving for current, since current squared, you have to take the square root of P over R. That's 120 over 450, gives you 0.52 amps. One more question. Again, we're not going to spend a whole lot of time on it. What is the power consumption of a flash bulb? This is 31. So you're given you're given current and voltage. So basically, you're going to use IV. Now, normally you use this equation when you're dealing with a resistor, either this one or that one. Okay, this will tell you how much a resistor, how much energy it's burning per second, its power. So will this. You have to measure the voltage here, here the current. This one you usually use when you want to find the power delivered by a battery to a circuit. V here will be the voltage of the battery. Sometimes they use they call it EMF, and they use this script E and write it this way. Okay. So in this case, you are using this equation, but you can use any of them for anything that you want. And so that equation IV is over here, 1.7 watts. And finally, I think there's another one here. In this case, you're given resistance and power, and you're asked to find current. So basically, you're going to use resistance and power and current. This is those three in there. So you will use this equation here. Again, you solve it for current. So you have to take a square root because you have an I squared here. And finally, the last problem, I squared R. 30 volts is applied across a resistor, and it generates 600 watts of heat. Let me turn down this. Got the sound too loud. And so the equation you're going to use here is going to be V squared over R, and you get 1.5 ohms to answer this question. All right, one more unit, one more comment about power. There is something called a kilowatt hour, which you may have seen on your electric meters. Don't forget, what is a watt? It's a joule per second, and kilowatt means thousands of joules, thousands of watts. So a kilowatt would be, like 1 kilowatt means 1,000 joules per second. And if you multiply this by time, right, then you get energy used. Okay, so a kilowatt hour is basically a unit of energy, not of power, because you multiply it by time here. So that's the last thing for that chapter. We're going to go on now to not that, but we're going to talk about circuit diagrams. Again, I know this is something you've been doing to lab. I know the lab in physics 2 is completely out of sync with the lecture, because you start building circuits very soon and you don't get to it in class. Okay, so if you build circuits, we already know what some of these look like. A resistor physically looks like this, but if you put it into a circuit diagram, it looks like this. This indicates that it's a resistor. A battery indicates this. This is the positive terminal, the longer one, and this is the shorter one. And a wire is just a wire. So simplest type of circuit, which I showed you already in the simulation before, would look something like this. One resistor connecting across the battery, and there will be a current running through here, and the current is given by Ohm's law, that the current is equal to the voltage of the battery divided by the resistance. Raising the voltage increases the current. Raising the resistance reduces the current. More resistor you put in here, a higher resistor, current will get less in the circuit. And of course, this is all controlled by Ohm's law, which can be written a number of different ways also. So as I mentioned before, a battery, which provides actually the force to move the electrons through these wires and through these resistors. Sometimes it's referred to as the electromotive force. In fact, it's what we call V, but sometimes they call it the electromotive force. Charge moves around, and when it gets back, we saw before, the much lower potential energy is lost. It loses potential energy every time it goes across a resistor. The battery then gives it another boost of energy, and it goes again. This is the way of looking at it. So this is what we call electric current. And there's an electric field created by a difference of potential. We saw the same electric field that we talked about earlier in the semester. Between the two terminals of the battery, it propagates at nearly the speed of light these electrons to go through the wire. Okay. And so we can draw that simple circuit that I had before. Instead of drawing a resistor, we can put something in here that looks like something you're using, like a light bulb, for example. And again, how much resistance this provides can be sort of looked at as looking at water flowing through a pipe. The pipe is pretty thick here. Water flows pretty freely. This is a valve. You can close the water or open the water. That's like a switch in a circuit. You can open the switch or you can close the switch and permit water to flow. When water hits a resistor, it has resistance to flow. That's like water going through a narrow pipe. Okay, it goes through a narrow pipe, it slows down the whole flow of water. And the battery is like a pump that's pumping the water through these pipes. So this is a good model to look at. And we already talked about how to use the meters. Voltage, you measure with a voltmeter. You put it across something. You always measure the change in voltage. This gives you the change in voltage between 2 points. And the ammeter, you have to put it into the circuit. You have to break a circuit, put it in to measure the current. And the source that maintains the current is, in fact, the battery itself. And uses units of volts. This is the EMF, is the work done per unit charge to transfer electrons. Now, in circuit diagrams, there are two ways to add a second resistor to a circuit. One is putting one resistor after the other. This is called series connection, or one parallel to one another. This is called the parallel connection. The difference between these is this. So current flows through here from the positive to negative, and it flows through there. Now current goes through this resistor, and then it goes through this resistor. So in a series circuit, the current is the same through all resistors in series. It's the same. Because don't forget, this current's got no place to go. It's got to slow down here and here, but generally it's going to be the same slowing down for both of them. Here, it's different. The current comes in here, let's say I, and it splits up. Part of it goes up in this direction, that's called I1, and part of it goes this way, in this direction. Let's call it I2. And I, the total current flowing through the circuit, is equal to I1 plus I2. Okay. So if the current splits up at any time, then they're parallel. If it doesn't split up, the same current flows throughout, they're in series. So in order to figure out in both these situations, what is the current, you must reduce, don't forget, what tells you what the current is Ohm's law. The current is the voltage divided by the resistance. But this only works for one resistor. Okay, if you have two resistors, 3, 4, 5, 10, it doesn't work. You must have one resistor. So in some simple circuits, you can find the equivalent resistance of all the resistors. The equivalent resistance, R equivalent. You can replace let's say the two series resistors with just one, which is the equivalent to these, or the two parallel resistors, which is one, which is equivalent to these. It's a different way of doing them for both. And so let's take a look at this type of circuit. So this is a circuit. We have 3 light bulbs and connected to a battery with a switch here. And this is exactly the same here. There's a switch here. There's 3 light bulbs. They're connected to a battery. You throw the switch down and current starts flowing. The same current goes through every one of these, even if they're different light bulbs. The same current goes through every one. The power spent in each light bulb depends on the resistance of the light bulb. It's that current that's flowing through all of them, but they may or may not have different resistances. They may have all the same. They may be identical light bulbs, or they may be different light bulbs. Now, the thing is, if they're in a series circuit, if one of these lamps blows out, that's like opening a switch here, okay? Except it's not here. The switch may be down, but it's going to break the circuit if one of these burns out. So that's like opening a switch over here, okay? And therefore current will stop flowing. We're going to try to answer what happens to the light intensity of each lamp, or what happens to the current as we add more lights, more bulbs into the circuit. So let's take a look. So this is the analogy we use. Let's assume that these light bulbs are identical and they're connected to a 12-volt battery. Okay, 12 volts. Okay, so what does that mean? That means when I close the switch over here, the electron starts going from the positive through the switch. It's got a lot of energy. It's like it's at the top here. It's got a lot of energy, and it's going to drop. It's going to drop when it goes across this bulb. It's going to drop. It's like dropping over here, 4 volts, because it started at 12. And then it goes through the next one. It drops another 4 volts. 4 volts because these are identical bulbs. So the voltage across each one is going to be the same. And then it drops across this one. And then, of course, it's on the ground. It's petered out. But the battery comes to the rescue, gives it energy, and it can start again on the other side. Okay? So basically what the battery does when it hits the ground here, the battery does work to bring it back up, and hey, here we go again. Okay, so this is a good way of looking. This is a gravity analogy to the flow of electricity. Now, this assumes, for example, that the lights are identical. Well, let's say they're not identical, they're different. Like in this little drawing here. These two R's, well, here they're identical, all right? And again, they're connected to a 12-volt battery here, 12 volts. Oops. So as you go from A to B, you drop 6 volts, and A could be like over here, in this picture here. You drop from A to B, you drop 6 volts, and as you go from B to C, you drop another 6 volts, and you're back on the ground, okay? And then you go up again. Now, let's say these are different now. These resistors are different. So what does that mean? Well, that means, depending on what the resistance is, if one of them is twice the other, for example, what will happen, it'll drop 8 volts on the first one and 4 volts on the second one. The whole drop is 12 volts. But the potential difference, if you put the voltmeter across, you will find delta V is 8 here, and it's 4 here, and it's 12 here. If you put the voltmeters across. But these potential drops have to equal the voltage of the battery. They have to add up to 12, and they do, as you can see here. So how to find the equivalent resistance in resistors? The process of reducing the resistance in a circuit is called finding the equivalent resistance. Okay, replacing these two by one. And yeah, I know you've done this already in lab. And so we know that in a series circuit, the current is the same throughout. The current, we're going to call it I. Let me do it in red. I. It comes out of here. How do you calculate that I? Well, you're going to use Ohm's law. And we just saw that the voltage is across this one plus the voltage across this one. Let's call this V1. Let's call this V2. These got to add up to V. Okay, they add up to V. The current is the same throughout, so we don't have to worry about the current. Let's just call it I. But these two voltages add up to V. We're going to use that fact. Okay. Let's say you have three resistors, the three different voltages across them, but they got to add up to the voltage of the battery, to V. Okay. The current is the same. So if the current is the same, means delta V across the first resistor here is going to equal I times R1, the resistance here. Delta V across the second resistor would be this same I times R2. The voltage across here is going to be the same I times R3, right over here. All of these have I in common. I can factor out the I, and therefore the total resistance is just the sum of all the resistors, the equivalent resistance. Very simple. If series resistors are in series, then the equivalent resistors is the sum of all the resistance. If they're in parallel, well, things are a little bit different. As I mentioned before, what happens, there's a current I coming out of here, okay? And this is the current that you get if you find the equivalent of these three resistors, voltage divided by R equivalent. Okay, this is the I you're finding here. But that I, whatever number it is, splits up into three. Okay, now if they're connected in parallel like this, that means the voltage across each one is in fact the same, because each one of them is connected across the same terminals of the battery. This one's connected across the battery. This one's connected across the battery. So the voltage will be the same as the voltage of the battery. We don't have to worry about this. Delta V, delta V, delta V, they're all equal to this. All right? So this is what this tells you. And all the currents add up. The I here equals I1 plus I2 plus I3. So, oops, going wrong way. Which is not the same as over here on positive resistors. And I should have had the slide. Actually, I'll come back to this because I put the slide somewhere else. So we're gonna do a couple examples using series resistors, and then we'll come back and finish up the problem. Is how do you find the equivalent resistors when they're in parallel, and do some sample problems. So let's go back here. So let's do an example. Okay, I'm just sort of organizing my notes here. So, as I mentioned, finding the equivalent resistance in this circuit in series is very simple. You add the resistors. 5 plus 3, 8. Now, if they're connected to a 9-volt battery, all right, so now what we're going to do is find, first of all, what is the total current in the circuit. So we know that the total current is going to equal to the voltage of the battery divided by that equivalent resistance that we just found. Let me tell you our total, all right, which we found, if you remember, 8. And so what is the voltage, what is the current that's running through every one of these? Well, use the formula. V is 9. So it's 1.1 ohms, amps, 1.1 amps, right? This is 9 divided by 8 is 1.1. All right, so now what else can we answer? Well, what is the voltage across R1? What's the voltage across here? Well, Ohm's law will tell you. We know the current that's running. We know the resistance. It's written right here. So what's it? For R1, it'll be that. Don't forget this was 1.1. And this is 5. What's 1.1 times 5? What's the closest number here? Right, 5.6. And you can see the whole problem here, right? The net resistance was 8. The current was 1.125. And the voltage across the first resistor was IR1, 5.6 volts. Well, how about R2? Well, you're going to do the same thing, right? Using the stuff we already found, net resistance and total current, same current, but now we're going to use 3 here. V equals R2, that's 3.4 volts. So 3.4 here, and in the previous problem we found to be 5.6. How much is 3.4 plus 5.6? 9. 9. They add up to this. How much power is used by R1? How much power is used up by this one? Well, you can use one of those equations. You can use any one because you know the voltage, the resistance, the current. You could use any one. The one I chose to use was IV. Power 1 is the current, and I don't put a 1 here, you notice, because the current is the same through everything, times V1. Or you could have used I squared R, because you know R, you know I that you already calculated. And you get 6.3. A would be the right answer over there. 6.3. Put this. It's hard for me to put it anywhere, right? I think if I erase this red stuff, oops. If I erase the red stuff here, I can put it right over the circuit. So there's one more problem here I wanted to do. So I wanted to calculate the power across R2 also, but I can't see it. So apparently I didn't do it in my notes here, but we'll do it without notes. Okay, how about R2, how the power in R2? So I'm going to use the same equation. Power in resistor 2 is going to equal the same I as we had before. And what was that I again? 1.1 was it? Yeah, 1.125. And we also, remember, we also calculated the voltage across here. And that was a couple of slides ago. Yeah, it was 3.4. So for the first answer, this was 6.3, I believe, right? Because we've got to remember those answers. Yeah, 6.3 watts. And this one here is 3.825. Now I'd like to think about how much power is delivered by the battery. Now the battery is over here. We're going to use a simple formula. The power delivered by this electromotive force is equal to EI, which is E is the voltage of the battery. Remember, usually when you talk about the battery, you can talk about it like this, EI. So basically E is 9 volts, I is 1.15. This is approximately a little over 10.1 watts. So this power that's delivered by the battery is used up. Some of it goes to this guy, some of it goes to this guy. Here's the sum. But they all got to add up to this. So the 6.3, except for rounding off errors here, plus 3.825 add up to 10.1. I think it does. It's going to be not exactly because of these decimal points that come up here. So we're going to go on to, we've done all that. And again, if you have a bunch of resistors here, you can do the same thing. You add up all the resistances, they add up to 18 ohms. So you can replace all of these with this one resistor. If this is 36 volts, then the current is going to be 36 divided by 18, 2 amps. And you can find the voltage across each one of these by multiplying I times R. I times R. This I, 2. 2 times 2 is 4. So that's the voltage across the first one. 2 times 4 is 8. That's the voltage across the second one. 2 times 5 is 10. That's the voltage across the third one. And 2 times 7 is 14. That's the voltage across the fourth one. So each time it goes across one of these resistors, it loses some of that 36 volts of energy that it had. Okay, so I am going to skip over this part, internal resistance of a battery, and go to back to what I started before, parallel circuits. So in a parallel circuit like this, basically, as I mentioned before, what happens is that the current runs out from here, but then it splits up among the three bulbs. If these bulbs are exactly the same, then 1/3 of the current goes to each one, like I have over here. And in this case, the potential difference, the voltage across each um, bulb is exactly the same because they're all connected really to the across the battery terminals. This point is common for all of them, and this is like the negative voltage terminal. This is like the positive voltage terminal of the battery. So they're all connected to this side. So the delta V is the same all the way across. But the currents are different. The current comes up here and splits up in three different paths. Now again, if these are identical bulbs, it'll split up equally. So again, we can sort of surmise what happens to the total resistance. So imagine we can say we can use the water analogy. So basically, you have water flowing through a pipe here that's narrower than the rest of it. It slows it down. But supposing you have two pipes like here in parallel, that means the water that's flowing up here, some of it goes this way and some of it goes that way. Is it going to be easier or harder for the water to get through here than here? Well, it should be easier because it splits up. So basically, it splits up into two. It's easier to get across now. How about a third pipe? That's even easier. So the moral of the story is that the more resistors you have in parallel, the easier it is the current to get through. In other words, the total resistance gets less and less and less. Yes, I know, we're adding resistors, but the total resistance is getting less. The more we add, the less the total resistance. So the total resistance is smaller than the smallest of the resistors. We'll see this formula in a minute. So we'll come back here. I left you off here last time when I was talking about parallel resistors. So we know that all the currents got to add up. I1 plus I2 plus I3, all the currents here are, the sum of them is equal to the total current. The voltage across each of these resistors is the same. So the first one here on top is going to be R1 divided, delta V divided by R1. This one will be delta V divided by R2, and this will be delta V divided by R3. So the current through each one of these, the current through this one is going to be delta V divided by R1, delta V divided by R1. The current through this one, this I2, right? So I1 is delta V over R1, I2 is delta V over R2, and I3 is delta V over R3. All right? Delta V is the same here. We can factor it out. And therefore, all of these add up to what's called the equivalent resistance. Equivalent resistance follows this formula. And if you use this, which we're going to do in a minute, the resistance becomes less and less the more resistors we add in parallel. So for example, let's do the same sort of similar problem that we did before. What is the total resistance in this circuit? It's connected to 18 volts, but doesn't matter because the total resistance is Look at here. Let's see if we can do that. Don't forget the formula is, let me bring it up. So this is going to be a little tricky mathematically the first time you do it. So 1 over r is going to equal to 1 over 3 plus 1 over 6. There's no r3 here, so you just 1 over 6. So you have to add these up. And usually I try to give you numbers so you can find the common denominator. So 1 over r is the same as 2 sixes plus 1 sixth, which is 3 sixes or 1/2. Now, this is a mistake students make commonly here. They say, okay, that means the total resistance is 1/2. No, it's not. This is 1 over the total resistance is 1/2. To find what R is, you got to invert this. Invert this, you get R. You invert this, you get 2. Not 1/2. Right, 2 ohms. And I know you probably know this from having done the lab, because I believe you already did do this lab, right? So, as I mentioned before, the total resistance of a bunch of resistors in parallel, and here there's only 2, the total is going to be less than any one. 2 is less than 6 and it's less than 3. The total will always be less than any one. So now that we find the total resistance, 2, we can find the current. Well, I guess before that, that's the next question, I guess. So what's the voltage across each resistance? Well, each resistance up here will have the same voltage. That's 18 volts. They're both connected across the battery. So 18 volts. Obviously, the next question is what I want to answer before. What is the current? Let's go back one. So what's the current that's coming out over here? What's the current that's coming out? This is not the question, but let's calculate it right here. Well, the total current is going to be the total voltage divided by the total resistance, which was 2, if you remember. Our total is equal to 2. The total voltage is 18. So 9 amps. 9 amps comes out over here, 9 amps. That 9 amps comes in here. Some of that 9 amps goes this way. I'm going to call it I1. And it'll go through this resistor. And some of it will go that way. I'm going to call it I2. And it'll go through this resistor. Okay, and so the next question is going to be, what is the current through R1? All right, let's see if we can figure that out. And I'll just write down what we know. We know that this I equals 9 amps. That means 9 amps comes in here. How much? How much goes this way? This is I1. This is I2. Can anybody figure this out? So I1 is going to be the voltage across R1, which is the same as 18 volts. They both have the same voltage, divided by R1, which is, this is 18, and this is 3. So 6 amps will go up here. Out of this 9, 6. So you already know the answer to the next question. How much goes this way? Well, the rest of it, which is 3 amps. All right, so this will be 6 amps. We just did that. And of course, through R2, you could have just figured out the rest of it, or you can say, okay, that I2 is going to equal to the voltage across R2 divided by R2. The voltage across R2 is the same as the other one, 18, and the voltage across R2 is 6, so that gives you 3. 3 plus 6 is 9, which is the current that's coming out from here is 9, do you remember? How about the power? Well, again, you can use one of the equations, a number of them. You can use, we know the currents through each of these. We know the voltage across each of these. We know the resistance. You can use any of those equations that you want. And you get the power that goes through here, power 1. And I have the calculation over here, so I'll show you. Okay. Then you can do the same thing for the other one. And then you can do the same thing for the power delivered to the circuit like we did before. Okay. So power 2 is 54 watts, doing the same type of equation here. And then the power delivered by the battery is going to equal to, again, electromotive force, voltage of the battery times the current it delivers to the whole circuit, the total current we found in the beginning. And that should equal the sum of P1 plus P2. All right, so this is 18 volts. And if you remember, the current was 9 amps. So you could check it yourself that 18 times 9 is equal to 54 plus 108. Now, as soon as we finish chapter 18, I will put up all these slides just the way I have it, with all my writing on it, so you can see exactly what I wrote there. So, one other type of application is to find the total current of a mixed circuit, where there are some resistors in parallel and some in series. So the thing to do is you have to add all the, I can't add this resistor until I replace these two with one resistor. Okay, so the first thing I have to do to find the total current here, I have to find the total resistance. So first I'm going to add these two. So the two in parallel, 1 over R parallel is going to equal to 1/3 plus 1/6. We already did that before. Those two result in R in parallel result in a 2 ohm resistor. So these two add up to as if there was one resistor here equal to 2 ohms. And that resistor is in series with this resistor, 4 ohms. So the total resistance in this whole circuit, it's not 6 plus 3 plus 4, but it is 2 plus 4, which is 6 ohms. So our total equals, let me just write it here, is equal to this 2 ohms plus the 4 ohm in series with it. So it is, the total resistance is 6. Now so that's like this whole thing is replaced with just one resistor of 6 ohms connected to this battery on the bottom there of 18 volts. This is 6 ohms. This is 18. What's the current running in this circuit? The total current, which is the answer to the question. The total current is going to be 18 divided by 3 amps. Okay, so here you see it on the bottom here, I guess. And you can do the same thing as you did before. You can answer a lot of different. What's the voltage drop across this resistor? Well, 3 amps flows, right? That's what we got in this question. 3 amps flows through that circuit. What does that mean? That means 3 amps comes out of here. That 3 amps comes in here and it splits up. This question, we don't have to answer that question. We're going to answer it in a bit, but we're going to answer what is the voltage drop across here? That's the first question, R3. Well, the voltage drop, don't forget, the voltage across here is not 18 volts. Okay. What is the voltage drop? Well, it's going to be IR. I being this number, R being this number. So what would be the answer here? Three times 4, 12. Okay, so you can see over here, calculation, using the 3 amps from the previous problem. Okay, so the next question is going to be, what is the current through R1? We could have sort of predicted that was going to be, what is the current through R1? So we have to go back. There's a number of ways of doing this, but the easiest way I think is go back and look at what was the one resistor that replaced these two. And you remember it was a 2 ohm resistor. So we're going to find the current through this 2 ohm resistor, the voltage across this 2 ohm resistor, and that'll be the voltage across here. Okay. Another way of doing it, we just found the voltage across here, right? It was 12 volts. This is 12 volts. We know what the voltage across this resistor is and this resistor. It's the same, but what is it? They add up to 18. So if this is 12, this has got to be 6 volts across here. 6 volts across here. Okay, now you could have just found by using this 2 ohm resistor, V equals I, which was, what was I? 3 times 2 is 6, right? I was 3, if you remember, times 2 is 6. Or we could have said these two got to add up to 18, so this has got to be 6 volts. And this will be the voltage across both of these resistors, all right? So again, this gives you the answer for the voltage across the 3 ohm resistor, and this gives you the answer across. But here they're subtracting 18 minus 12, 6 volts across here, and therefore the current will be 2 amps. Okay, I think I'm going to just want to do one example, and then you guys can have the pop quiz, because one of the questions in the pop quiz is something like, not this. Well, they both lead to it. Just reviewing, resistors in parallel add inversely. Don't forget, the total resistance in parallel is given by that equation, going to be smaller than either one of these. But what I wanted to do is just look at an example like this one here. Well, we're not going to do it here, but you'll have a similar type of problem on the pop quiz. So if you want to find the total resistance like this and something like this, you got to start from the beginning. You got to add all the parallels. In other words, you're going to add these two in parallel and replace them by one resistance, which you can draw here. Whatever the number is, we're not solving this problem, but 1 over R1 plus 1 over R2 equals 1 over R total, and this is 1 over R total. Then these three are in series, all right? So these are gone already. They've been replaced by this one here. And these three are in series, so you can just add up whatever you got here as a number, but not 2. It's going to be something less than 2. But you will add these up, and that's the total resistance. And then you can find the total current flowing through here. All right, I think I'm just looking at, if you need to know something to do all the problems here. I think you got everything here. All right, so I guess you guys are ready for the pop quiz. The only thing is I forgot the password. So let me take a look. Let me take a look at the password. We're over here, I think. Quiz 4. Oh, this password. Okay, that's the way. This password. So I'll put it up. I'll put it up. Okay, so let me